Good afternoon, everybody. Thank you for coming. We're going to spend the entire lecture talking about one simple molecule, H2O. Although the formula is simple, we'll see that the properties of this simple molecule are perhaps one of the most complex set of properties in all of nature. So I'm going to tell you something about myself only at the request of the organizers. I don't like to talk about myself, but I'm afraid they put all these titles under my name, which are true, but the real truth is I am fascinated by research, and I love to have puzzles to try to figure out. And we'll talk about the puzzle of liquid water in this talk. So let's go to the first slide, which I can do from here. I begin always my talks with dedication to the people who did the work or otherwise inspired me. There's actually 40 people, almost all of whom I have a paper in collaboration with, and all of whom have inspired me one way or the other. 10 names are in red, and those names are names of people who do experiments. I learned at a young age to pay attention first to experiment and then to try to understand, rather than try to understand and then look at experiment. So these 10 names have all actually made the discoveries that have motivated what I did. Starting with José Teixeira on the bottom line, because 30 years ago, I was fortunate enough to spend a semester in Paris in the lab of de Gennes, and he put me in the office of a young experimentalist named Teixeira. And Teixeira was making experiments on water. I was trying to do something totally different at the time. Being a theorist, I was trying to understand details of phase transitions, and here he was working on liquid water. I did not know anything about liquids in general, much less water. But when he showed me his data, it was clear that this was not a liquid of any typical sort. It was completely different than other liquids. Inspired by that puzzle of a little more than 30 years ago, 33 years ago, I have been fascinated by water and working on water ever since. The second thing I like to do in talks is give the take-home message right up front. And the bottom half of this slide has a very brief take-home message. The first point is that water is complex, unbelievably complex. And because of this complexity, or corresponding to the complexity, there are not one or two anomalies, but there are 69 anomalies. If you want to see them all listed, you go into Google and type two words, water anomalies. And you'll get many hits, but the very first one is a wonderful compilation by Chaplin of all the anomalies of water that he could learn about, and tentative explanations for some of them, but not all. So that's the motivation, if you will. The real question is, what is the take-home message? And what we will argue that makes water so special is not so much the hydrogen bonds. There are other materials with zero hydrogen bonds that behave like water, but rather the fact that the local geometry of a water molecule is tetrahedral. And that's tetrahedral geometry gives rise to two characteristic energy scales when two of these tetrahedra approach each other. We'll go through that in some detail. The second point, we'll introduce a concept which I named the Widom Line, and we'll see that when there is a Widom Line, it's often a smoking gun. That means a clue that there exists some sort of a critical point. And the third thing we'll talk about only briefly is that the famous protein glass transition is in fact quite likely nothing to do with protein, nothing to do with glass, and not even a transition, but rather it's a crossover in water structure when the system crosses this Widom line, yet to be defined. So let's go to the first slide, and the first slide is a quiz. I like to say for professors, because when I've presented this puzzle to faculty at various conferences, they fail invariably. What is the puzzle? They're shown a glass of ice water. There's a thermometer in the ice water, and the bulb of the thermometer is at the bottom of the ice water. And you can do this tonight, or even in your office right now if you have some ice water. Stick a thermometer in it and ask these famous intelligent professors, what is the temperature of the thermometer? And everyone learns that if everything is in equilibrium, then the temperature is 0 Celsius, or very, very close to 0. But in fact, if you do this experiment, it's not 0, it's far from 0, it's 4 degrees Celsius. And this is, we'll later see, due to the fact that water has a density maximum at 4, so that means the heavy, dense layers of water segregate to the bottom of the glass. You may wonder, how can that happen? Because most of you know that the difference in density of water and at 0 Celsius and water at 4 degrees Celsius is only 2 parts in 10,000. That's an incredibly small difference. And you might think anything that small can be ignored. And theorists, of course, love to ignore anything that small. But in this case, that tiny density difference is responsible, as we'll see, for life as we know it, and it's responsible for many, or at least corresponds to many of the anomalies of water, can be related to this simple experiment that you can do tonight. Okay. It's always nice to begin a talk with some puzzles. So now we'll begin the talk. All that was preamble. We'll begin the talk now. And the first thing to say is, what is the question? What are we addressing? And we are addressing the question of understanding the anomalies of water. One anomaly is relatively easy, and that is why ice floats. It's important that ice floats for reasons we'll see shortly, and it's also very bad that ice floats with only 10% of its volume above the water. Anybody who reads the newspaper knows that we just celebrated the 100th anniversary of the sinking of the Titanic. You imagine a ship that sees this little bit of an iceberg sticking up and then goes too close to the iceberg, and what's going to happen? It's going to scrape the rest of the iceberg, and if a scrape is bad enough, it'll burst and the ship will sink to the bottom, as the Titanic did. In fact, the Titanic has been found deep, deep, deep under the water. The second question is not what is the question, but why do we care? Why do we care to understand 64 or 69 anomalies of water? Why would we care at all about that? There are many things we don't understand that are and there's always two answers to this question. There's almost always a practical answer and a scientific answer. Well, the practical answer is, as everybody knows, that water is universal in all branches of science. We could not have life as we know it without water. We can poison a person by replacing H2O by simply D2O. Chemically identical, forming hydrogen bonds and everything else, but physically just slightly different. The second reason we care is scientific. It's fascinating that such a simple molecule, much simpler than any other molecule you'll ever study in chemistry, much less organic chemistry, is so puzzling. 69 puzzles. That's amazing. And the curiosity about water dates back a long, long, long time to Aristotle, who recognized it as a very special and unusual liquid, all the way to the present. And the third question is, so what? What do we actually do? And what we do will occupy the rest of this talk. We do, in the time-honored tradition of science, we make a hypothesis on some basis or other, and then we proceed to test it. And the we in this case is that large number of 40 people you saw on slide 1, plus a number of other people elsewhere in the world engaged in testing this hypothesis. So it's always conventional to begin any talk with a phase diagram. On the y-axis is pressure, on the x-axis is temperature, and we see, I'm supposed to use the pointer here, excuse me. On the x-axis is temperature, good. On the y-axis is pressure, and if we ignore this dashed line, we have a phase diagram that's typical of almost all materials. There is a first order line separating the gas and the solid. Moving across that line is called sublimation, the solid to become a gas. There's a blue line separating the gas from the liquid, and moving across this line is corresponds to condensation. And then the green line is the simple freezing line. Moving to the left from across this line corresponds to freezing. Water is unusual in a way that's fairly well understood because the slope of this solid-liquid transition line, instead of being positive, is negative. That follows from the Clausius-Clapeyron equation, which all of you probably know about, so I'm not going to describe it in this talk. If you don't, it's worth Googling it and learning why. It's a very common exam question to ask a student, why? And if the student cannot answer, it's a very common response to fail the exam. Having failed a few students for their ignorance of this an explanation of this simple fact. Now there's one extra line here labeled Widom Line, and I'll tell you what it is later, but it's named after Benjamin Widom, one of the fathers of liquid state physics, modern liquid state physics, and in fact the inventor of scaling hypothesis. And Benjamin Widom taught me about this line, or at least the idea of this line, about 45 years ago when I was a student, and I haven't forgotten. I found my lecture notes, and that's where it was. And okay, now I have to find the little buttons here. So now we're now going to examine this phase diagram in some detail. First, we'll take a slice of it at constant pressure. So there's only one variable, not two, and that's the temperature. And I think every child knows that water is stable between 0 degrees and 100 degrees Celsius. And every cook knows that if you use a pressure cooker, you can get water well above 100. That's practical because the vegetables cook quicker if the temperature is above 100. And everyone who's ever tried to measure the temperature of water in the icebox knows that water does not freeze at 0 Celsius if it's reasonably clean, but instead it freezes at some lower temperature. And below 0 and above freezing is called supercooled. Technically, it's metastable in the sense that enough shaking or something nucleating can make the water turn to ice. But if we go lower than about minus 40, then then water is no more water. It freezes. It must freeze. This is called the homogeneous nucleation temperature, T sub H, and water stays frozen all the way down. So then what are these funny words like glassy water? Well, if you prepare low temperature, very low temperature H2O by putting it in a hose with a very fine nozzle and squirting this nozzle on a liquid nitrogen cooled metal plate, then when the little tiny droplets of water hit the plate, they lose their kinetic energy very rapidly and are therefore sort of arrested in the configuration that they had back when they were water. So they start in the structure of water, and you quench them by dropping them on tiny droplets on a plate, and they form a solid, but the solid has almost identical structure as the liquid. So this is known. Everything here is true. 100% true. No one quarreled about it. It's been known for decades. Okay. Now comes a hypothesis. Everything here could be rubbish. No one knows. And this hypothesis was discovered by a brilliant graduate student, Peter Poole, 20 years ago, working in my group, and a brilliant postdoc, Francesco Shortino, also working in our group. And both of them were computer specialists, so they decided to do very accurate simulations because the power of computers had just in that year, 20 years ago, taken a quantum jump forward, so they could do things with a computer that they previously could not be done. And what do you think they did? They decided to explore the entire phase diagram at all pressures, That's what this axis is. So on the y-axis is temperature as before. You see all the same phases, 0, minus 38, and these temperature down around minus 140 where you get the glassy water. But now they put pressure on, and I think most people already know from the experience of the ice skate or perhaps other things that the melting temperature goes down slightly when you pressurize. But so also does the homogeneous nucleation temperature. Okay, that's not of itself so surprising. What's very remarkable is that they discovered a first-order transition in the glassy water region, that as pressure was applied, when the pressure got bigger than approximately a 1 kilobar, that's what this 0.2 of a gigapascal is, 1 kilobar, the low-density solid water, low-density glassy water, A stands for amorphous, so low-density amorphous water, undergoes a first-order transition and suddenly jumps to a different structure altogether. And that different structure is called high-density amorphous water. And these structures have very little in common. So this was a big surprise you could have a first-order transition. This was discovered in 1992 by the same pair of people, Poole and Shortino. Furthermore, a computer has one virtue that some people would say is a drawback, but the virtue is that you can simulate for times shorter than the nucleation time, and that means this nucleation event in the solid ice region, the so-called no man's land, is no more a no man's land because water stays liquid, it doesn't freeze up to a certain number of microseconds. And in the microseconds, a long time scale for simulation, so one can study the liquid in this region. And what they discovered is that this line of first-order transitions between the two forms of glassy water extended into the no man's land, separating now not glassy water, but two liquid water phases, a low-density liquid, LDL, and a high-density liquid, HDL. And this line of transitions extended smoothly, and then stopped. This was a line of first-order transitions, just like this is a line of first-order transitions. And many of you know that with a few exceptions, but very few, lines of first-order transitions terminate in critical points, just as we saw a minute ago, where the liquid-gas transition in water terminated at its liquid-gas critical point, so also the LDL-HDL transition terminates at a critical point above which there's no difference between LDL and HDL. The organizers warned me that I might need a cup of water. I have a cup of coffee. It's a little cold by now, but it's better than nothing. Yeah. It's a good idea. Thank you for giving me that suggestion. So is this clear? This is a hypothesis. Some people called it a speculation at the time because, first of all, their only evidence was simulations. And simulations have a characteristic that you get out what you put in. You put in a model of water that, of course, is not water. It's just an imitation of water. And you get out what you get out depends on what you put in. And as I sometimes like to say, garbage in, garbage out. So this hypothesis was greeted with shall we say, a huge amount of skepticism. I don't want to tell you stories because they'd fill the hour, but instead I want to talk to you about what comes next. So the first test, I'm going to go through 20 tests of this hypothesis. The rest of the talk will be 20 tests, and we'll learn a lot independent of whether their hypothesis is correct or not. I think it is correct, but we'll learn a lot about the results that are uncovered by neutron scattering and by other forms of measurement like IR and Raman. So the first test was carried out by Alan Soper and Maria Antoinetta Ricci already about 10 years ago. And what they did was they said, how could you have two forms of water? This seems absurd. Two forms that differ from each other, not just in smooth way. Obviously, when you pressurize anything, it gets a little more dense. That's true of everything, because the compressibility is always positive. So under increasing pressure, the volume always must get smaller. But that's not what I'm saying. I'm saying a first-order transition with two distinct forms of water. This is a experimental result of their findings. At high pressure, they have one structure, which when you make a ball and stick model, looks like this tetrahedron. This is only one of them. And at low pressure, you have another structure, which when you uncode it, looks like this. And this structure, the low-density structure, abuts another low-density structure in such a way that mimics the structure of ordinary ice cubes in your icebox. That is to say, the structure of solid water at atmospheric pressure. And in contrast, this structure mimics the structure of high-pressure ice, say ice 6. There are several ices that have this structure. What's in common to these two structures is the very local, out to 3 angstroms, geometry around every water molecule. Every water molecule has a bond of length about 3 angstroms to the next water molecule, and the 4 water molecules around each water molecule are arranged very close to the tetrahedral angle. The angle is almost precisely 109 degrees, and the length is almost precisely 2.8 angstroms. So there's not much freedom there. However, the ways in which you can bring together two of these little pentamers, if you want to call them that, because there's 1 water in the middle and 4 around it, are 2 in number. One way is the way that makes ordinary ice, where the water molecule here lines up with this one in the same plane, and you have a hexagonal ring. And all of you have seen photographs of ice, regular ice, atmospheric pressure ice, with these famous hexagons. That's a low-density structure, and we know that density of water is about 10% bigger than the density of ordinary ice. And we also know the diffusion of low-temperature water when it's in this form is lower, okay, and that it's very locally structured. In contrast, the high density is like these tetrahedra. One of them rotates 90 degrees and straddles the other one, sort of my colleagues say you should call this a tango configuration, because if you've ever seen tango, it involves this sort of coupling between the dancers. And this structure is less structured because whereas this has no freedom to wobble, this tango structure, if you've ever seen tango dancers, indeed has the freedom to wobble. And the density of this is about 15% more, 1.05 grams per cubic centimeter. Okay, so this is experimental fact from 10 years ago, and it's not been questioned, or at least not been refuted. So, one thing to have 2 well-defined phases, as we saw here, 2 well-defined local structures, and it's another thing to have an actual phase transition between them. Soper and Ritchie found measurements at every possible pressure, but they did define 2 totally different structures, but they couldn't make measurements at every pressure, and therefore we could not see an abrupt first-order transition. But it's consistent with the possibility of an abrupt transition, and therefore the first question is, how could you ever have a first-order transition in a one-component liquid? Never been heard of before. And I have a wonderful grandmother who always asked me very difficult questions. And she always, whenever I saw her, said, "What are you doing nowadays, Gene?" And when I came back from Paris, all excited about water, she said, "How does a gas know when to condense? How could this happen?" And I took a stick and drew in the sand the interaction energy between 2 molecules, which has a repulsion, as we know, and an attraction. And I explained that there was cooperativity. I told her what that is, so that when 2 or 3 molecules get close, they have a lower energy, and more others join. And she said, "Well, excuse me, why did you only draw 1 minimum? Suppose you had 2 minima, like here. And here's the same picture, but with now 2 minima. a deeper outer one, what do you think would happen? Well, she knew the answer. At still lower temperatures, from this single liquid, this liquid would condense out a second liquid. And since R is bigger, the density is lower, so this well number 2 is the ordinary ice from the ice box, and well number 1 is this high pressure ice. So I'm not using my thing, am I? Good. Okay. Test number 2. If the key thing is this local tetrahedral symmetry, and not hydrogen bonds, as Linus Pauling taught us, then we would expect to find this in many, many, many different liquids which have tetrahedral symmetry. And there are other such liquids. The most common liquid on Earth is silicon dioxide, which, as you know, has a tetrahedral local geometry. And this most common solid, probably, or most useful at least, is silicon. And other people pooled the same pool while he was a postdoc with Austin Angel and another former student, Sastry, and Ben Widom's son, and experimentalists have confirmed that silicon also has this liquid-liquid transition. So what happens when we cross this line? Well, with simulations, we learn that as you start to cool water, you cross a magic line called the Widom Line. The Widom Line is the locus of correlation length maxima, and response functions like the compressibility and specific heat are proportional to powers of the correlation length, so they should also have maxima. And that's indeed what's found. Let me show you this. Here is early experiments from 40 years ago from the Austin Angel group, and on the left side is our data on the specific heat at low temperatures. And everyone knows the specific heat is large for water, but most people don't realize that it, like most liquids, decreases on cooling, and then below about 30 Celsius, it actually increases, and increases a lot. You see here about 40 or 50% from its minimum. And similarly for another response function, the compressibility. Like most liquids, the compressibility decreases on cooling, but below 46 Celsius, it actually increases again by about 40 or 50%. Furthermore, these increases can be fit by power laws, where there appears to be a singularity temperature, Ts for singularity, at a temperature that's below the homogeneous nucleation. It's about 228. And homogeneous nucleation we saw was at 38 Celsius, so that's about 235. So you can't get down to the a critical point because the line of homogeneous nucleation, it forms a fence that you cannot go over, but the fact that data fit a power law means there has to be a reason. And if there were a critical point, this would be a sufficient reason. In fact, it's not only, so what do these thermodynamic response functions tell us? They allow us to quantify fluctuations. For example, the compressibility quantifies the fluctuations in specific volume. And we see here that same, this is a schematic of the data I just showed you with a minimum at 46, and that the fact that the compressibility starts to increase means that the volume fluctuations are actually no more decreasing, as our intuition would tell us, and as is true for typical liquid, but they actually start to increase. Similarly for specific heat, that the specific heat corresponds to the entropy fluctuations, and the entropy fluctuations, as in almost all liquids, decrease as you lower the temperature, but below 35 Celsius, they start to increase. And finally, there's something very remarkable, and that's the cross fluctuations. Of volume, that's this, and entropy, that's that. And these volume entropy cross fluctuations are proportional also to a thermodynamic response function called the coefficient of thermal expansion. And for all materials, this is positive. But we just saw that for water below 4 Celsius, this function goes negative. And all three of these response functions can be fit with the power law with the same fitting temperature, the same apparent singularity temperature of roughly minus 45 Celsius. So the question is, why do we have this apparent singularity? What is going on? And before we try to answer what's going on, let's just answer a different question. Why do we even care if there's a liquid-liquid transition? Is this just some idle curiosity not related to the price of butter? Of course it's related to the price of butter, and that is why it's interest is that if there is a critical point, we learn that that's the end of the story, and above the critical point everything is all over, just one homogeneous phase. But this is completely false. Above a critical point, there is this Widom line, which is the locus of maximum correlation length, where functions look like they're diverging, as we just saw a minute ago, and then have maxima, and then come down again. So there's lots of activity going on up here, and furthermore, it doesn't happen only near the critical point, but up to 2 or 3 times the critical point, there can be anomalies. So if there's a critical point, it might be sufficient to explain all the anomalies of water, such as the 3 I showed you, of specific heat, compressibility, and coefficient of thermal expansion. Okay, I'm going to skip this. So let's make another test. Let's look at simulations. I already warned you that you get out what you put in, and you can put in all different models of water. They go by funny alphabet soups, ST2, TIP4P, TIP5P, and so forth. All of these models have the property that they support this original picture that Poole and Shortino got using the ST2 model. This picture is verified for every one of these models with the possible exception of an understructured one called ST2. Called SPC. SPC, you can't get low enough in temperature to see this, and therefore you cannot draw any conclusion. Okay, now, simulations is one thing, you get out what you put in. Experiment is something else. So let's turn to experiment for most of what remains in this lecture, and we'll look at experiment. The very first experiments were done just 2 years after the Poole-Shortino work by the father of amorphous solid water, Mishima. And what Ichiro Mishima found was that if he went to glassy water and pressurized it, he could undergo a first-order transition to a different form of high density of amorphous water called high density amorphous water, and furthermore it was reversible. He could relax the pressure and he would go back to regular. So he found 2 well-defined, experimentally well-defined phases of amorphous water. To the extent that amorphous water is just very cold, unmobile, non-mobile, liquid water, this is already a very striking evidence that you might have 2 forms of liquid water. And I should add that Mishima won the highest prize in Japan, called the Nishino Award, for this experiment, plus one other. And this is the other experiment, which I was fortunate enough to be his sort of lab assistant, and he put my name on the paper. And that has to do with going back to this picture and forming a path, making measurements along a horizontal path. That means at fixed temperature. And when you cross the phase transition curve, you expect a latent heat. And the latent heat will be recognized by a sudden change in the temperature. So by simply pressurizing water at a fixed temperature, we can get circles like this circle, where'd my arrow go? This circle, and at a higher temperature this circle, and a higher one this circle, and they map out a first-order transition line. And what do you see here? You see that at low temperature there's a well-defined kink, and by the Clausius-Clapeyron relation, that means we're in one phase here and another phase here. The high-pressure phase is obviously the high-density liquid, because pressure always induces an increase in density. And The low pressure phase is the low density liquid. At very warm temperatures up here, there's no kink at all. So from these data, we infer this phase diagram. Here is the line of hypothesized liquid-liquid transitions separating LDL and HDL. Here are the two lines I just showed you with kinks, and here's the third line with no kink. And that locates not exactly where the critical point is, but a range of temperatures and pressures between this line and that line, but it's fairly striking evidence that bulk water has properties that are consistent with the hypothesized liquid-liquid transition. You get something else out of this. If you remember, the most boring thing in thermodynamics, at least for me, was the Gibbs phase rule that told you that when two phases are in equilibrium, the Gibbs free energy is the same for both. So let's go back and have a peek at these picture. We have here two phases in equilibrium, a high pressure, high density phase and a low pressure, low density phase. So when they're in equilibrium, that means that we know that the Gibbs potential is the same. But the Gibbs potential for the ices has been tabulated. So we end up knowing the Gibbs potential of the liquid. And when you know the Gibbs potential, you can differentiate it and get the volume. And therefore you have the volume, which is shown on the y-axis here, as a function of temperature and pressure. And this is so-called equation of state. Here's our low-density liquid, high-density liquid, low-density amorphous ice, high-density amorphous ice. And here's the critical point, a hypothesized critical point, where there's no more a difference between the two liquids, LDL and HDL. This is also Mishima's work. My job in this was mainly, I think, just to pump, because you had to pressurize slowly, and it had to be done by hand. Okay, so this is maybe a time to stop very briefly for a question, because we're going to come to the second half of this talk. I don't want to take a lot of questions now, because the best is yet to come. But you can type in a question if you like, or you can just say, go onward. As I don't see any questions, maybe there's nobody listening. That would be it. It would be a possibility. And I can say anything I like for the rest of the lecture. Okay, here we go. Now there's a big remaining challenge. And that is how to enter the no man's land below -38 Celsius and stay in the liquid phase. The experiments of Mishima were not in the liquid phase, they were in the solid phase, and what one was observing was solid water interacting with an extension of the high density forms of solid ice and giving rise to those kinks that we saw. However, we'd like to do experiments on real water. And there's two answers to that. One, many of you know about it, that Anders Nilsson, one of the best experimentalists working on water, is making measurements in slack on falling droplets of water. And because they fall into a chamber where the temperature is below the homogeneous nucleation temperature, this means that for a short period of time, they don't freeze. They don't freeze because they're very tiny, and to freeze you need nucleation. So if you let fall a lot of drops, a goodly number of them won't have any nucleation sites, and it will stay liquid. And during this tiny bit of time, while they're falling, you can make measurements, and that's what Nilsson did. And he'll report those measurements in due course, so I'm not going to report his work, but instead I'll go back 64 years earlier to a Bible. The Bible I have in mind is the General Chemistry book of Linus Pauling. My father was a chemist, and I was 6 years old when this was published, and he was at the time a student of chemistry, and he learned about this book, and he brought it home to me and started telling me the wonderful clarity that Linus Pauling wrote and the mysteries he wrote about. And one of the mysteries was this mystery shown right here. Shown on the y-axis is the melting temperature of water, H2O, and then the three materials right under it in the periodic table. H2S because S is under O, H2 selenium because selenium is under sulfur, and H2 tellurium because tellurium is under selenium. And as you see, there's a nice smooth trend of these three. And one of the brilliant things of Pauling is to realize that when you have a nice smooth trend and it's suddenly broken, there has to be a reason. So here's the trend and here's the break. And the break is well outside experimental error. If you extrapolated this, water would have a melting temperature about minus 100 roughly. And in fact, we know it has a melting temperature of 0 Celsius. So there's a 100-degree break. That's a big, big break. So how do you explain that? Well, Linus Pauling explained it. He said water is stabilized in the solid phase because water, H2O, has hydrogen bonds, and these materials do not. And these hydrogen bonds, so to speak, keep the water molecules in the orientation and position of ice. They sort of hold it in like a straitjacket holds in a person who's mentally deranged. And therefore, Linus Pauling pointed his finger to hydrogen bonds as being the key thing that makes water special. Now, much more recently, Professor Chen at MIT and his many brilliant graduate students, one of whom is now a professor himself, Professor Zhang, who will speak in 2 days from now, same time, same station. I urge you to listen to his lecture. And Professor Chen's group realized that if you could somehow prevent these hydrogen bonds from forming, you might have an H2O, modified H2O, if you will, naked H2O, no hydrogen bonds, that had a melting temperature down around minus 100, or at least a lot lower than 0. And now, how can you do that? How can you strip water of its hydrogen bonds? Well, the first answer would be that's impossible, completely impossible. But that's not, whoopsie, something missing. You can do that by nano-confinement. If you confine water in very, very tiny pores on the order of 10 molecules across, let's say in round numbers 20 angstroms, 2 nanometers, then the hydrogen bond network cannot get fully formed. And this would be very nice, because then you could study stripped water. When I say stripped, I mean of its hydrogen bonds, one of its key features. It's almost like taking the clothes off of the emperor. The emperor without clothes doesn't look like an emperor, and water without its hydrogen bonds, Linus Pauling would say, is not water. But that's not strictly true, because if we're studying the properties of H2O that don't depend on hydrogen bonds, then stripping away the hydrogen bonds should not matter. So what did Professor Chen and his collaborators find out? Here's one of the things they found out. They found out that when you make measurements, now this temperature is well below the homogeneous nucleation temperature. You can see if water melts at 273, and so here's water in its melting temperature, bulk water melting temperature, and what you see is the intensity of infrared absorption as a function of frequency. The black curve is the full sample, and as you can see, it's a little asymmetric. And you know, one of the famous things for people who do spectroscopy, one of the famous things they do, always made me a little uneasy, is to decompose something that looks almost like a perfect Gaussian into many Gaussians. And that's what this shows. Here's one Gaussian, which has a peak at exactly the frequency, 3120 wave numbers, that low-density amorphous solid has. And as we argue, that should be exactly the same as low-density amorphous liquid, except for mobility. So there's the LDA peak. And here, at 3220, the brown curve is the HDL peak. HDL, why do I call it that? Because the frequency is the same frequency as the frequency of HDA, which has been measured by many experiments by them. So this is at room temperature, at freezing point, which is room temperature many places. And soon we'll be in Boston, where I am. It's going down below this temperature tonight. And this is at 20 degrees below freezing, which we get once in a while in the winter. And this is at 40 degrees below freezing, and 50 degrees, and 67, 80 degrees, and 90 degrees. And what you see happens, notice that the LDL peak starts to rise, and the HDL peak starts to decrease. And here they're almost equal, and at this magic temperature, about 225 Kelvin, they're almost the same height. Now, remember that number 225. We'll see that that number pops up over and over and over again. And what you can imagine, if these two peaks are the same height, is you have roughly equal amounts of the LDL and HDL, as you would at a critical point. And if we keep going down, then we get more LDL and less HDL. And we go to the lowest temperature before you freeze is lots more LDL and lots less HDL. So let's look at this in a somewhat simpler way. And this is the same exact experiment, where now instead of looking at the peaks, which are messy and debatable and everything else, we look at the area below the peak. That's another time-honored trick of spectroscopists. So we look at the area here under the brown peak, that's the HDL area, and we'll compare with the area here under the red peak. And we can see here that they're roughly the same at the hypothesized critical point. Let's see what happens when we look at them. Here at very, very high temperatures, we see a very small amount of HDL, and a very big amount of HDL and a very small amount of LDL. And as we cool, the amount of LDL increases and the amount of HDL decreases, and they cross right around this magic number of 225. And below that, the same trend comes in the other direction. So this is fairly striking because it's not based on some complicated subtlety, but it's based on area. Area is relatively insensitive to tiny mistakes, tiny inaccuracies. Okay, let's move on to say. So as soon as I introduce this confined water, a natural reaction, and many chemists have this reaction, that the confined water is totally different than the bulk water. They're just two different materials. Well, of course they are. Confined water is not bulk water, otherwise it would freeze. It freezes 100 degrees lower. Whatever it is, it's not bulk water. But that does not mean that all its properties are totally different. Only the freezing property is different. For example, this green curve is a fit to data, real data, on bulk water. You see the legend says bulk. And as you see, going into the supercooled region, the ordinary density, has its maximum at 4 Celsius and then continues to decrease. We even argue that it can be fit with an apparent divergence as it decreases to minus infinity. And so that's the behavior of bulk water. And the red circles are the actual measurements on confined water. And as you see, first of all, they agree with the bulk water, as they better, but they might not have to. So they agree with the bulk water, but unlike the bulk water, they don't stop at about minus 35 or so, where the bulk water stops, but they just keep on going down, 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 down. There's actually a density minimum, which the Chen and Malamachi groups discovered for the first time in water way down below the hypothesized critical point, after which the density becomes fairly more or less like a normal material. So as regards this property, confined water is the same as bulk water. And how could that be if there's no hydrogen bonds? And that's simply because the properties of water depend on water. They don't depend only on the hydrogen bonds. Some properties do, but not everything. Good, okay. Now, where is my clicker? Go beyond. So here is now the derivative of that curve. The derivative, you remember, was called the coefficient of thermal expansion. That derivative is, as you can see, negative here, then it becomes 0, and then becomes positive. So what we plot here is the coefficient of thermal expansion. It's negative, negative, negative. It becomes positive and goes up, and then it has a maximum just when the system crosses the Widom line at about minus 35. And then it comes down again. And as you saw, it crosses through zero at the 205 Kelvin, which is the temperature where the density actually starts to increase again on further cooling. So this response function here is got the properties, as you can see, of any thermodynamic function crossing the Widom line. At a critical point, this would go all the way up and diverge to infinity. And it's well known that the behavior of the derivative of the density does diverge to infinity when you reach a critical point. Now let's look at the specific heat, a second response function. Let's start with the data, and we saw that the data of Angel and his collaborators showed a specific heat that was fairly flat and then started to rise, but in both couldn't get any lower temperature than around minus 35. But in contrast, with the confined water, we can go as low as we want, and sure enough, there's another maximum at exactly the same magic temperature, 225, the Widom temperature, if you will, and below the Widom temperature, the fluctuations come down again. So what's happening is that above the Widom temperature, we have mostly LDL, mostly HDL, as you saw, and when we reach the Widom temperature, the system is roughly 50-50, that's what we just saw, and therefore the fluctuations are a maximum. Just as when you throw a coin, if the coin is fairly weighted, then the fluctuations are a maximum. If the coin is not equally weighted, say 80% chance for heads and only 20% for tails, the fluctuations are much smaller. So the fluctuations are a maximum when it's 50-50, just as we saw when we looked at those experiments with FTIR. And then they come down again. That work was corroborated by experiments in Boston by two very gifted graduate students, Limei Shu, who is now an associate professor at Peking University, and Pradeep Kumar, who is now on the faculty of the University of Arkansas, working together with Professor Chen and now Professor Poole, and Professor Buldarev, and now Professor Shortino. Okay, let's go on. We could skip this if you want, but we've been saying that the liquid is continuous with the low density amorphous solid. And that's what this curve shows. It's merely the data for the full width at half maximum of the experiments that we've been looking at, the FTIR experiments, and this is the decrease down to the lowest temperature you get even in confined water. And then these are experiments that the Stuart Rice group made long time ago of low density amorphous solid. And you see there's a region where there are no data, but it's at least plausible that these data are continuous with these data, further supporting the idea that low density amorphous solid water is nothing other than the extension of ordinary water to low temperatures. We can skip this, I think. And we now come to one of the first experiments that the Chen group did way back in 2004. And that experiment was a remarkable, oops. Let me go to them. I'm going to do them historically order. I have to do this one first. Nope, I can't do that either. Okay, these are experiments not by the Chen group, but by the group of Malamachi and Messina. And what's measured is a Arrhenius plot. That means the logarithm of the inverse diffusion coefficient as a function of inverse temperature. So if you're not accustomed to these plots, you have to do two reciprocals. Inverse temperature is easy. It means lower temperature means go to the right. So as we go to the right, we're going colder and colder and colder. And if we measure the inverse diffusion, that means diffusion is getting smaller and smaller, as it should. So the diffusion constant's getting smaller. But look at the rate it goes. It's got an upward curvature here, and below, again, the magic 225, the data are on a straight line, as in an Arrhenius plot is a straight line, or as use the modern terminology of Angel, this corresponds to a strong liquid, and this corresponds to a fragile liquid. Now, what does that have to do with the transition? Well, we know that the LDL at low temperature is very rigid, and it's therefore should be like a strong liquid, and that the HDL is very floppy and should be like a fragile liquid. So these are data from Messina on NMR measuring the diffusion coefficient. Now let's look at the similar data, only this time from MIT, the group of Chen. Sorry, this slide is small. If you're not using your full screen, this is a good chance to use the full screen. And you see here on the top half, you see just a repeat of what you just saw, the Messina experiments of Malamachi group on self-diffusion. And here on the bottom half, you have a different experiment, not measuring self-diffusion, but measuring the alpha relaxation, not by NMR, but by quasi-elastic neutron scattering. So totally different experiment, measuring a totally different thing, but you see exactly the same phenomenon, a fragile liquid crossing over to a strong liquid, and moreover, the crossover point is exactly the same temperature, this magic 225, or as I like to call it, the Widom temperature. Furthermore, this Widom line, if it is a function of the pore, and if the people who say confined water is different than regular water, if that were true, then that was my cell phone, which I put underneath me now. I forgot to turn it off. If this was a function of the pore size, then we could say indeed the pores make a difference. But notice that the same fragile to strong occurs with the same crossover temperature, 225, for a wide range of pore sizes, 10 angstroms, 12 angstroms, 14 angstroms, and 16 angstroms. So for me, this is one of the best refutations of the stubborn idea that confined water is just totally different than bulk water. This is an absurd statement. It's different in some ways, but it doesn't mean it's totally different. Okay? Onward. Now we come to another word, and that is that confined water is confined in silica walls. MCM41 is the acronym given to the little tiny pores, little tiny microcapsules, microcylinders which confine the water. And as it's only 10, 12, 14, 16 angstroms across, you could easily say whether the walls are all polluted because silica leaches into the water. And this may be true, but again, we don't know that a little bit of silicon kills these strong anomalies. So, but still one worries. So the Chen group had another good idea. What they did is they said, throw away the silicon, let's confine water by something else. And already nature has provided us that, because everyone in this room knows that proteins are surrounded by a layer of water. And that layer of water is sort of bound to the protein. Without that layer, by the way, the protein cannot even function. And DNA, the same story. These are schematics just showing the water around these biomolecules. So if really confined water has this property, then you would expect the similar behavior for the confined water, and indeed you find the similar behavior. Find exactly the same behavior for the confined water. And moreover, the temperature at which these anomalies occur is exactly the same. Here is, for example, one of the classic experiments where one measures the mean square displacement as a function of temperature, and mean square displacement is a function of temperature. At very low temperature has a solid-like looking form with a very low slope, and then it suddenly around magic temperature of 225, there's an abrupt change of slope and a much bigger slope, if you will, corresponding to a rigid or strong LDL fluid crossing over to a less rigid HDL fluid. And similarly here, this is the characteristic time which is measured, and the same thing happens, a crossover at around 225. In the protein water, this is not confined in glass, silica glass, but it's confined by protein. And very recent results from the Chen group show that you don't even need a biological molecule. You can do this experiments all over again in cement. Everyone knows that water finds its way into cement, and it's of course confined on a very small scale. That's why it doesn't freeze. And you can go down at low temperatures and make these same measurements on cement, water confined by cement, and you get the same curves. So the property has nothing to do with being the property, this, if you will, fragile to strong crossover, has nothing to do with protein, nothing to do with anything except the property of water. And the property of water that matters to see it is that the water is confined enough that it does not freeze. Zhang that. He speaks in 2 days. He's the one who makes these measurements. But, I mean, being a simple theorist, I would say you simply measure the amount of water that's in there and weigh it before and weigh it afterwards. But I'm sure there's something much more complicated and subtle. There are many ways to measure density. So I honestly don't know the answer to that. And I see the second question from Hong is the size of the confined water or the silica pore size. I thought I said the silica when I showed 10 angstroms, 12, 14, 16, all the way up to 20 angstroms. So that tells you the pore size, and the properties were independent of pore size. So now when it's confined by a biological molecule, it's in a sense not really confined. It's just a layer of water, or of several water molecules, but it's not something with a uniform distance because it depends on which part of the surface of the protein you're at. A hydrophobic part may have less water around it, and a hydrophilic part of the protein may have more, but the key thing is that the amount of water doesn't matter. What matters is it does not freeze. To prevent water from freezing, you got to follow Linus Pauling, 1947, and bust up that hydrogen bond network. And you can bust it up by many different ways, and confining water is one such way. You cannot form a hydrogen bond network infinite and HCl and HDL water, unstable states. Not unstable, they're very, if anything, they're metastable, but metastable means it's the same as stable. You simply move the coordinates of the system in such a way that if you waited an infinite amount of time, something would happen. It would condense out. And how fast we should cool it down? How fast do you cool it? Well, that's a good question also. You're asking me experimental questions there again, and I defer also to Professor Yang Zhang, who's speaking in 48 hours from now, 47 hours from now. I hope he's writing all these down so he can answer them. But I'm not aware that the cooling rate is so critical for the glass state, the cooling rate is critical. But to simply get the two forms of water, it's quite sufficient to simply cool. You don't have to do it in a huge hurry. If you want to make a glass, you've got to capture the liquid before it has time to recognize that the lowest energy state is a crystal and rearrange the molecules to form a crystal. That means you have to quench it very fast. That's why I said you spray from a little micro spray, little tiny droplets of water on a plate cooled to nitrogen temperatures so that the cooling rate is huge. I don't know what number, but numbers like 10 to the 5th kelvins per second stick in my mind. But I don't even know how to think about 10 to the 5th kelvins per second. I guess you could think about it as 100 kelvins per millisecond or something of that sort. Okay, we're almost done, and I know that the organizers are going to throw me off the stage soon, and Professor Zhang will probably talk about this tomorrow anyway. However, I want you to advertise one of the most dramatic experiments I know, which is his experiment, I think while he was still a graduate student in the Chen group. And this experiment is the analog of what Mishima did when he demonstrated 2 years after this hypothesis that the two forms of amorphous solid water, HDA and LDA, had a first-order transition between them. So the question that Yang Zhang asked is, I'm supposed to have two forms of liquid water, HDL and LDL. Then I should be able to do the identical experiment and see the identical hysteresis. And that's what you see here. The bottom curve is at 1 bar. That's there's no hysteresis because we're clearly in the one-phase region. Nothing's happening. At 1,000 bars is a little bit of a difference, hardly outside experimental error. By the time we're up to 1,500 bars, there's a big difference. And here's, and you remember we hypothesized the other data were consistent with a critical point around 1,000 atmospheres. So this is just right at the critical point. This is a little below, and even more below. So, and you see the two curves are cooling and warming. That means if we cool down in temperature, moving to the left, we have this black curve, and if we warm it up, we have this red curve. And this difference is the hysteresis that's characteristic of first-order transitions. We can skip this. And we can probably skip this because these are experiments still underway. But the simulations were done by the same Kumar, who was a graduate student here, finished about 3 years ago, but the paper was just published a few months ago in Nature Scientific Reports. And that was a paper that calculated with simulations the scattering you would expect as you lower the temperature. Let's not worry even about what kind of scattering is. This is the famous peak, if you will, the Rayleigh peak, and these are the wings of the Rayleigh peak, and they're monotonically decreasing at high temperature. But below the Widom temperature, they're not. There opens up a second sideband here, and this second sideband is presumably, we interpret or hypothesize, is a consequence of this liquid-liquid transition. And the reason it's a consequence is if you have a rigid second phase setting in, then you'll have new vibrations characteristic of this second phase. And that's the interpretation. The experiments were started by Yang Zhang and Meng and others in the Chen group, and the definitive experiments are going to be done shortly. So stay tuned, and you'll probably see a famous paper coming out in a number of months from now. I think the experiments are scheduled for fairly soon. Neutron experiments. Okay, so what have we done? A little bit of a summary. We've argued that this hypothesis, based only on a simulation, if you will, an imagination coupled with a simulation, has a number of experimental facts consistent with it. So let's do the last and most striking. This is the end of the talk coming up. And the end of the talk is to take a look at this first order line. Let's go back one just so you, well, here's the first order line, blah, 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 this much, and coming down in pressure. And here is the critical, hypothesized critical point. And here's the Widom line extending from the critical point. And this is simulations of the ST2 model. So nothing's hypothesized. Everything here is found for the model. And that means the first order transition line is found, the Widom line is found, and the critical point is found. Since everything is there, we can sit at any state point and sit and watch as a function of time. And what do you think would happen? Well, if the system were infinite, and we stood on one side of the first order line, the system would be in one phase. Let's say at high pressure, it would be in the high density liquid. At low pressure side, it would be in the low density liquid. But if we have a finite size system, the system would be expected to flip back and forth from these two phases, as if the system could not make up its mind whether it wants to be in the high density liquid phase or the low density liquid phase. So let's look at it as a function of time when we pick one state point, not all these points, there's 350 little marks here, but only one of them, reasonably near the critical point, and we watch as a function of time. And so this is the last and final test, number 20, and here's the density of the system as a function of time in nanoseconds. So there's a very long simulation, 200 nanoseconds. In the old days, when this started, you'd be lucky to get 200 picoseconds. So this is 1,000 times longer. And what do you see here? You see the density flips from the high density phase, you remember was 1.05, to the low density phase, you remember was about 0.9. And then it flips back to the high density phase and back to the low density, and high density back, not quite, back to high density, all the way down, up, down, up, down, up, down, very chaotically. Then it just goes into complete chaos. If we shine a flashlight from the left to the right, we see this projection here with one big peak at around the high density value and one second peak at the low density value. And so this is what time dependence shows you. And the little pictures up here are snapshots. This snapshot is in the low density phase, and the blue corresponds to well ordered. This color scheme is a measure of the local order in the liquid. So where you see blue, it means well ordered, as in LDL. And where you see red, you see that points to the red, you see less well ordered, as in the HDL. So as a function of time, we expect the system to flip from well-ordered to less well-ordered, and then back again, because that's what you see here. Well-ordered to less well-ordered, and back again, and back again, and back again, at all different time scales. Furthermore, if you know anything about phase transitions, you know one of the most striking things is a system is not uniformly low density and uniformly high density. That's not the case. If that were the case, all these balls would be red, unstructured, and all these balls would be blue, structured. But instead, there's a huge heterogeneity. In fact, a measure of the size of the homogeneity is the correlation length, which is only on the order of a few water molecules. So let's now do to the last thing. The organizers will put up the movie. I have a wonderful movie that was done here by this man, where's my pointer? A graduate student named Tobias Kesselring, and more recently working with another graduate student, Eric Lascaris, and all these people were holding the ladder, as we like to say, so these graduate students could do their work. But the video I'm going to show you is done entirely by Kesselring, in part because I wanted to see it. I never saw a phase transition happening in my life on a microscopic scale. Of course, we can freeze water and make ice cubes. We've all seen that. But we don't see what each little molecule is seeing. So now we're going to become Maxwell demons. We're going to jump inside this water, and we're going to watch what happens. So organizers are going to put up a movie, and while they put it up, I'm going to tell you how excited I am by it. Wait, don't start the movie. Up, stop it. Anyway, you saw a tiny bit of the movie, and I think you saw enough to see there were little tiny, very local clusters of 4 or 5 water molecules in this low density phase, and then they break up as a function of time and form little clusters of the high density phase with more red than blue. So there's a little like Republicans and Democrats. In our country, Republicans are recognized as red party, and the Democrats are recognized as the blue party, and politics is a little like water because everyone's cooperative. If everyone thinks, for example, that Obamacare is a mess, and then they'll tend to propagate that belief among their friends, and then conversely, if it turns out it works, and everyone says, oh, it works fine, they'll propagate that belief. And we all know that's how it works. And the extreme case would be in the case of Nazi Germany, where so many people believed what Hitler was saying that everyone became red. Now, you're going to show me my movie again, if possible? I don't need my pointer. I won't ask for a pointer. Here comes my movie. Now you can see the blue. You see the blue. Now, look, as a function of time in the order of a few nanoseconds, the Democrats are losing ground to the Republicans. All those households that were Democrat, some are staying Democrat, but many are becoming Republican. And the brighter the red means the more right-wing the Republican. They're, if you will, Tea Partiers. Whoops, but now we're coming back to Democrats. Liberals are taking over. We're halfway through this movie, so keep watching it, and very soon you'll never see it again. See, now the Republicans are taking over. And the Tea Party people are rearing their heads loud and clear. and they're winning, but now the Democrats say enough of that, return us to power, and the blues are coming back. That's it. That's the end of Kesselring's movie. And I think that's the end of my talk. Let me check if I have anything else except to say thank you for listening. Yep, I only want to repeat, I want to leave on the screen the take-home message, which we saw was two characteristic length scales corresponding to the way two tetrahedra come together. The Widom line, when you see one, is a smoking gun for some critical point, and since we're in the one-phase liquid region, it has to be a smoking phase gun for the liquid-liquid critical point. And finally, the protein-glass transition is not protein. It even occurs in cement. It's not a glass at all. No sign of a glass. Nothing to do with the glass. And it's not even a transition. It's just a crossover in water structure as you lower the temperature, where the water structure changes from more HDL-like at higher temperature to more LDL-like at lower temperatures. I put again my collaborators up here, and I say thank you for listening. Questions? Question from me. Is the ice we see in our daily life LDL and or HDL? And the answer is we're above the critical point, so we don't see either one of those. We're in the one-phase region. But the local structures of every water molecule we see is more like one or more like the other. But I read the question again. It's not the water we see, it's the ice we see. The ice we see is like LDL, because the ice is ordered at atmospheric pressures in this local configurations of LDL. However, at high pressures, the ice is ordered in a different configuration, exactly that of HDL. So the question is the ice like LDL or HDL? And the answer depends on pressure. At normal pressures, it's like LDL, and at high pressures, it's like HDL. It's hard to read and talk at the same time. Are LDL and HDL unstable states? No, not at all unstable. How fast should you cool? That's what I said. I'm not sure, but I've seen numbers like 10 to the 5th Kelvin. But I'll ask Yang Zhang to see if he'd be willing to answer that question for me. And I'm sure the organizers will give him an extra minute to answer it. Emmanuel, what is the difference between amorphous HDL and LDL and supercooled water HDL and LDL? And the answer is no difference whatsoever in structure and any static property. However, a huge difference in time scale, because the HDL and LDL are liquids. That means they're displaceable. The time scales are the time scale of liquids. And the solid HDA and LDA, which you ask about, are solids. That means they have a much, much slower time scale. And therefore, in fact, even hold together. Colorado School of Mines. When lyophilizing, sometimes meltback occurs when the glass transition forms. Is this due to the Widom line? Oh, I'm ashamed. I don't even know what meltback means. And so you made a very interesting idea. I don't know. It could be correct, and it could be not correct. I don't have an answer to that. I wouldn't have guessed. It's related, but I don't quite know what meltback is. Yu Zhang, another question. Are LDL and HDL liquid? Yes. If ice is solid, why ice is LDL? Because solid and liquid refer to time scales of flowing. We know a solid because it flows very slowly. A glass, for example, flows on time scales of centuries or even millennia, and liquids flow on much shorter, orders of magnitude shorter time scales, but they're the same darn thing. Silica glass and molten silica are the same, effectively, as we know, because if we watch a glass blower make a glass object that you buy in a fair to give to your friend, then you see the liquid silica plunged into a bucket of cold water and quenching the motion of all those little particles so they stay in place and form a glass. The same way that LDL is made by quenching water. And so the answer is LDL and HDL are liquid, but at the right temperature becomes a solid. If you cool slowly, you get a crystalline solid called ice 1H, which and local structure of LDL is the same as the global structure of ordinary ice tray ice in your refrigerator. Someone's typing. Then, is normal ice crystalline or amorphous? Normal ice is crystalline. We're going to do X-ray diffraction from normal ice, and the peaks that you see in X-ray diffraction of cold water persist, only they become delta functions. Hardly any difference. And of course, they persist in larger distances. If you can picture, if you haven't seen it, just Google that structure factor or X-ray scattering or neutron scattering from low temperature water, and Google the same thing for ordinary ice, and you'll see no difference whatsoever except sharpness. And I have now. In essence, HDL and LDL refer to amorphous water. Amorphous water is amorphous. Liquids are amorphous. Even the word amorphous is not well defined. Amorphous on what scale? On very small scales, we saw that in that last movie that there is structure, but only out to 2 or 3 molecules. The correlation length in that movie was on the order of 8 angstroms. And that's been measured experimentally by the same José Teixeira, working with Louis Bozio, and I was fortunate enough to be also a co-author of that paper many years ago, demonstrating that ordinary water had a correlation length of about 8 angstroms, very short. If you were at the right pressure, you see, remember the critical pressure is around a kilobar, or at least something a lot bigger than atmosphere. If you were at the right pressure, then that correlation length, as you cool, would get large without limit, would go to infinity. But since we're at atmosphere pressure, the correlation length gets larger and larger until you cross the Widom Line, which is the locus of maximum correlation length, only 8 angstroms, and then it decreases again. So you may say, what's 8 angstroms? 8 angstroms is nothing. But that's not true at all. Short correlation lengths don't mean nothing at all. In fact, almost everything in nature has short correlation lengths. It's very hard to adjust the system right to the critical point. So HDL and LDL are both amorphous waters, and depending on the pressure, they can be less amorphous, so to speak, as the correlation length gets bigger and bigger. I think this concept of local short-range order compared to infinite range order of a crystal is a very overlooked concept in the education of students. I did not understand this until I had been a long, long time. I want to thank you all for listening, if you were listening, and if you are having a well-deserved afternoon nap, then I'm glad you had a well-deserved afternoon nap. And that's what I can do now that I'm done. Have a good evening, and I hope to see you.